receive less than, you can see the answer is 2 millirem per hour. Now, what's the difference between a Röntgen, a rad, and a millirem?
Started thinking about that actually the other day. Well, millirentgens are only in air, right?
Yeah. Röntgens are in air, and they're only for X-rays and gamma rays. Okay, but the good thing for us is that a Röntgen is almost equal to 1 rad. Okay, because what is a Röntgen? What is it equal to? How many?
Ergs per rad.
100 per square centimeter.
Okay, well let's go back again. Okay, a rad is 100 ergs per gram. Okay, and so it happens that 1 Röntgen is about 97 ergs per gram. So plus or minus a statistical deviation, they just make equivalent. So then what's a rem?
Equivalency in man.
Röntgen equivalent man. Okay. Okay, it's what your radiation badge units are measured in, because that's also a important question. Okay, how do you calculate rem? Mr. Singh, how do you calculate rem?
I don't know, Mr. Rocky.
How about Ashley? Do you know how to calculate rem?
Is it through Siebert?
Well, no, because a Siebert is,
Great.
yeah, it's that's using grays, and but you need to. Well, it's not Becquerel either.
No.
Okay, now, okay, you guys, remember that you're graduating in what, 6 weeks?
Yeah.
You guys are the authority on radiation in your hospitals right now. So, Mr. Andy, what is a REM? How do you calculate REM?
It goes with secrets, I know that, but I don't know.
No.
It's a grazing?
No. Okay, REM is our traditional unit.
Are you talking about Rem and Silver?
Well, REM and Sieverts are the same things. They're used interchangeably. But remember that REM is the traditional unit and Sievert is the international unit. Okay? So my question is, they're both, you need to understand how we calculate it. So I want to know what is it that we need to know in order to calculate REM. Because we have effective dose equivalent and dose equivalent. They're both very similar, dose equivalent and effective dose equivalent. You need to understand what the difference is on that too. So let's talk about what is the dose equivalent that you would be using for this. Mr. Villa. No, how do you calculate REM? What is the difference? We know that Röntgen is exposure in air. We know that it's a certain amount of electrical charge produced by the ionization of the air. We know that it only works for X-rays and gamma rays. What energy? What's the maximum energy that I can look at when I'm doing Röntgen?
3 megavolts.
All right, 3 MeV. Okay? Because otherwise you don't have a detector large enough to get the electrons that are produced. Okay? So, I need to know what parameters are we measuring with dose equivalent and effective dose equivalent. That would be important to know on a board exam, you think?
Multiplying absorbed dose in rads by the relative biological effectiveness, RBE.
That's close. Okay. There's 3 ways you can do it. Okay. The radiation absorbed dose multiplied by a quality factor or a radiation weighting factor. Remember the WR? Rads times WR, which is the weighting factor for that particular type of radiation. And if we're talking about effective dose equivalent, then we have the rads, we have the quality factor, and we also have the sensitivity of the tissue. Okay? And that's more what they're going to nowadays, is what we call the effective dose equivalent. Okay?
Is that rad times quality factor?
Yeah, it's rads. Actually, the correct way that they put it now is rads times the radiation weighting factor. So rads times WR. But that weighting factor is based on the quality factor or the RBE. Now remember, quality factor, we measure the amount of ionization that takes place in a certain volume of water. Okay? We measure the ions that are produced in there. With RDE, we actually expose tissue. So we have tissue in Petri dishes. Now, the other thing is you need to know what is the standard type of radiation that they use for this. In other words, when I'm comparing, say, a neutron with another type of radiation, what is the standard?
250 kbp X-ray?
Right, 250 kbp X-rays. So we expose the water or the tissue sample to 250 kbp X-rays. We calculate the number of Röntgen, which then gives us the number of rads that it absorbed. And then we expose it to the radiation that we're trying to determine the quality factor for. Okay? And then when we're talking about the tissue sensitivity, after they expose the radiation to a group of cells, they physically look at all the cells and see what percentage of them have damage. Okay? And damage can be anything. I mean, any kind of an effect you produce as a result of the radiation is considered an effect on its sensitivity. Okay? Next one down here, okay? According to the NRC, imaging rooms should be posted with which of the following signs. Now again, most of these signs are based on how much radiation intensity there is at a distance of 30 centimeters or 12 inches. Okay? So down here, all of a sudden we have a radioactive materials. So when would you put that up there? Huh?
In a lab,
Why would you put it in the lab?
that's where they're stored.
Okay. Well, remember, we're not going to put this sign up until we have a certain amount of radiopharmaceutical. So the fact that you've got 25 millicuries of technetium in there doesn't mean that you have to put up a radioactive material sign. Okay. In Ann Steve's book, it shows you the list of the quantity of radioactivity that you have to have in order to put this sign up. Okay? You may have more than one sign up there. You may have radioactive materials because you have a quantity of it, and then because when you do your daily surveys, you may have one of these other signs up here. And remember this one here, grave or very high radiation area, that's the one where it's more than 500 rem per hour. I've never seen one, but I'm sure if I did, I would not get very close to it.
On some of the handouts, you've been kind of like interchangeably using millirems and milliroentgens, so they're kind of equivalent, right?
Yeah. Yeah, the reason why is because X-rays and gamma rays both have a quality factor in RVE of 1. So if I have 1 Röntgen and I multiply that time, or if that's equal to 1 rad, I multiply that times the quality factor of 1, then I have 1 rem. So basically 1 Röntgen equals 1 rad equals 1 rem. Okay. But remember that for the most part now they're not using the Röntgen. It's actually becoming an obsolete unit. So you'll be using rads for the most part, because remember that rad is for any type of material and any type of radiation. Okay. The other thing over here, okay, have a spill in the hot lab, radiation is 115 MR per hour, which of the following signs should be posted? Okay, then notice caution, high radiation area. Okay, anything over 100 MR per hour. Okay, the next one. Okay, according to the NRC, a sign with the words caution, very high radiation area should be posted in an area where you could exceed in an hour, and that's 500 rads, or 500 rem. Okay. It doesn't really matter because if you're receiving 500 rads of neutrons or 500 rads of alpha particles, you're probably going to be dead anyway. In fact, even if you got 500 rads of X-rays or gamma rays, you're probably not going to survive that one either.
Does that one go by the sign grave danger also?
Yeah.
The 500?
The next, okay, which of the agencies regulates transport of radioactive material? Okay, and obviously that's DOT. Remember they have type A and type B packages. Which ones are the ones that you normally get?
Type A.
Right, you get type A. Okay, if you had a nuclear bomb sent to your department, then you would probably have it in a type B. Okay? Normally when you have really large quantities, very nasty radioactive material, then you don't want to ship it in a type A container. Okay, then to determine your transportation index, okay, that should be posted on all of your shipments, especially your yellow 2 and yellow 3. And remember, that's your radiation reading at 1 meter from the surface. You're also supposed to have posted on that label what radioactive materials are in there. Okay? And then you as the technologist are supposed to open up the package after you make sure that it's safe and verify what's in there, that it's what you ordered. Okay. Next one here. Okay, at the surface, 0.4 MR per hour. At 1 meter, no detectable radiation. Okay, so that's going to be a white 1. So basically, non-radioactive stuff is shipped to us in a white 1. And like I said, the people that write most of the questions for your board exams contributed to the questions that you're seeing here. So it's not going to be the exact question, but it will be very similar to it. Okay. So now we have a package. Okay, at the surface it's 12.9 and 0.9 at 1 meter. Okay, what's the limit for the surface? Don't be guessing, guys. Remember, you guys are the experts. All right, 10 MR per hour. And in your book on page by the way, on page 9, it shows you when you have to put up radioactive material signs. So it's based on a quantity. Actually, it's based on a couple of things, mainly the quantity, the energy of the radiation, and the half-life. Okay. And then your packages. Let's see here, where is the packages at?
So the limit for camera is 10 MR?
No, I don't like the way that they wrote when they did the new book here. Writing is so small. Hey, Cheney, I'm not used to the. But here's you need to recognize these labels too, okay? So notice 50 MR per hour and 1 MR at 1 meter. And then not more than, you should never have anything more than these levels here. This is the maximum for anything, regardless of what you ship. Okay. Anytime you get more than 200 MR per hour, you've got a problem, or 10 MR at 1 meter. Because the way they're supposed to shield this, you're not supposed to exceed either of these. This is on page 4. And again, you should be able to recognize these labels. Because when you either throw this stuff out, you have to deface them or whatever. Okay. And it's really cool to put these in the windows on your car, but you'll have a lot of explanation of the highway patrol. Of course,
That's so bad.
people have done that. We had students a few years ago that did that, and they got caught. Yeah, you do not put radiation warning signs in your car. I know it looks cool, but you know.
It's just saying out loud.
Yeah, my daughter has kind of a radiation.
Biohazard signs.
Biohazard signs are better. Just put one of those there.
Is that illegal?
Probably. Yeah, they're going to think you're some kind of a terrorist or something. Okay. Now, the next one here, okay, notice it says, which of the following exposure rates indicate that a package containing radioactive material should be labeled category 3? Again, this one exceeds the 50 MR per hour at the surface, so automatically, regardless of what it reads at 1 meter, it doesn't mean anything. So this would be your one here. Are you guys just kind of making sense?
Yes.
Okay, so you can imagine that, you know, especially somebody like me asking you questions, I might give you a reading at the surface that is, you know, 49 MR per hour, which, you know, makes it a category 2, but then at 1 meter, okay, it give you a higher value at 1 meter, so that you would have to make it a category 3. You have to look at both of those. Make sure you read the whole question, okay? The people that write these are even more sneaky than I am.
How's that possible?
How's that possible if they're more sneaky than I am?
No, how's it possible for it to like at the surface level have a certain reading and then at 1 meter have like?
You might have like a beta gamma emitter, or you know. So I mean, sometimes it just, you know.
For category 3, it lists here at the surface for 200 milliroentgens per hour.
Right. But look, what is it at the surface?
At the surface is 200.
Oh, 200 MR per hour at the surface.
Yeah.
1 meter is 10 MR.
Okay, so I think at 1 meter,
10.
Technically.
well, the category 2, what's the maximum for category 2? 50.
50.
Yeah, so that's more than 50. So, I mean, when they're saying 200, it means it cannot exceed.
Full level.
Yeah, so 50 up to 200 is what is going to be category 3. So that's the reason for it there on that one. Okay. But again, unfortunately, the people who write these test questions are not as nice as I am. They don't give you the formulas for a lot of this stuff. But I want you to kind of see the type of questions that they're asking, because this is what you can expect, especially in radiation protection. Okay, again, category 2, okay, you notice this would be a category 3, right? In fact, when you're going through these questions, you might want to put down, it's a category 3 because this is more than 50 MR per hour at the surface, okay? This one here, 52 MR, again, it's more than that at the surface. Okay, this one is less than 50 MR per hour, so there's your category 2. What would this one be here? 0.5 MR per hour at the surface and no detectable radiation, 1 meter.
Category 1.
Yeah, category 1, white. Okay. It says, okay, which of the following must be maintained until the radioactive material license is terminated? Okay. Waste disposal wipe. So anything you send back to your radio pharmacy. What about your radiation monitoring records, your dose records?
Until your license is terminated.
Yeah, until the hospital collapses, or you know, I'm sure 100 years from now they'll still have your records somewhere until that radioactive material license is no longer there anymore. Okay, according to the NRC, records of all the following must be retained for 3 years except. Okay, and the bioassay is because that is similar to a dosimetry reading. When would you do a bioassay on somebody? Okay, I-131, mainly liquid. Okay, they don't care about the capsules as much as they care about the liquid. What you do have to keep in mind, though, is with the capsules, you never want to handle them because a lot of times there's external contamination on them. You know, when you're trying to load those little granules of lyophilized I-131, lyophilized means freeze-dried, then it can be contaminated on the outside surface. But the liquid is the big problem, because remember, the liquid is volatile. Iodine is very unstable, and the hotter it is, the more iodine gas you have. So that's why they keep it refrigerated. Then the next one, okay, so NRC regulations for personal monitoring records, we already said those have to be indefinite. Okay, NRC requires that all the following information must be included on the unit dose measurement, except, yeah, we don't need the dose calibrator does not have to be on your record of radiopharmaceutical administration. Okay, because your unit dose, what's the rule on unit doses? Do you have to assay those before you inject them into a patient?
You don't have to,
Okay. But see, a lot of people,
but you should.
yeah, most people do. Okay, because you might be getting gypped. Okay, they may be charging you for 20 millicuries, but there might only be 15 in there. Okay. And the next thing is the NRC decay and storage records must include the date and time of the radioactive materials. I'm sorry. According to the NRC, decay and storage records must include the date that the radioactive material was placed in there. Okay. I don't know. I don't see a lot of people doing that. But normally, like I say, for your medium length or your medium half-life radiopharmaceuticals, you know, like gadolinium, indium, thallium, those are all, you know, that's the other ones. Technetium is going to be gone in a day or so anyway. Then, okay, the NRC records of survey instruments must include. Okay, now if you utilize the state of California for your radioactive material license, then basically it's a very, you know, it's an involved process. That's why most people just have it sent out to a company. You send it out to York Medical Physics and they do all this stuff for you. When they're talking about, okay, the description of the calibration procedure, you have to tell them what sources you use. And if you remember that survey instruments have to be calibrated on both sides of the scale. So basically you have a low reading and a high reading. Okay. Within the correction factors, again, some instruments are capable of reading other types of radiation, but you have to be able to correct for it. Okay. And then the exposure rate. Okay, what is an exposure rate, guys? Remember, we had a whole chapter in the math book about this. So what would be an exposure rate?
The exposure rate formula with the gamma constant.
The gamma constant, yeah. Remember that each radiopharmaceutical has its own gamma constant, and that's why they tell you that when you have certain amounts of radioactivity, there's certain procedures that you have to follow. One of the ways that you can calculate that is by knowing the exposure rate constant, and then dividing that into your radiation reading. That'll tell you how many millicuries of spill you have, so to speak. Does that make sense? Remember, like, let's say that you have a reading of 1.1 R per hour at 1 meter. Okay, the gamma rate constant for technetium is 0.590 R per hour at 1 centimeter. So the reading that I just described to you would be approximately 2 millicuries of technetium that's spilled. Okay? I mean, I don't really, you know, normally anytime you detect a spill, nobody's going to go in there and figure out, you know, what the heck it is. They'll just try to clean it up if it's safe. And as you decontaminate and get the levels down to where there's no more removable contamination, then that's as far as you normally go. So you keep using filter paper until you no longer pick up more than 22 disintegrations per minute per centimeter squared. Da-da-da-da-da-da. Okay, next one here. Point source produces an exposure rate of 30 MR at a distance of 15 centimeter. What is the exposure at 40 centimeters? Okay, what procedure would you use for this?
That's is it the inverse square law?
Okay, that's the inverse square law. So if we were going to calculate this one out, remember I told you that it's I1 D1 squared is equal to I2 D2 squared. Okay, so you have 30 MR, and then 15 centimeters squared, and that's equal to x at 40 centimeters squared. Okay. So if you have your calculators, hopefully you guys all have calculators. Bring your calculators from now on because we'll probably be doing a lot of calculations.
Can we use our calculators during the test, or do they provide it for you?
They'll either provide it for you, so long as it's not a programmable calculator, you can use it, I think.
I'm pretty sure they provide it for you.
Yeah.
Yeah, but they
The
don't have
question
the
is,
lock
you need to
and
make
stuff.
sure you know what buttons are used for what purpose.
Exactly, that's why it would be easier to use our own.
Yeah.
Well, on some calculators, you know, you can just enter the numbers and then the function and just kind of go through like a sentence in a paragraph. But on other ones, you have to enter the function first and then enter the numbers. So you got to make sure you have the calculator that you know how to operate. Okay. Did you all get 4.2 MR per hour? Okay. Again, and then sometimes, like I said, if you had a mean, nasty teacher, they would ask you at what distance would you get a certain radiation dose. Or, you know, so in other words, let's say that we were talking about you had a radiation reading of 30 MR per hour, but you want to move that radiation far enough away to where you have a reading of only 2 MR per hour. So how far would you need to move? Okay, does that make sense? Because that's what you're usually dealing with in a hot lab situation. So if we change that, okay, we have the 30 MR per hour times the 15 squared, and then that would be equal to 2 MR x squared. Okay, so 30 times 15 squared, I'm guessing that this is what, 165?
Mm-hmm.
Is that 165?
6750.
What is it?
6750.
6750.
6750?
225.
I was going to say, yeah, that seems too high.
225.
Okay,
Oh,
so,
no, I was giving you the 30 times 225.
okay, so 30 times 225 is equal to 2x squared. And people, please remember that when you're using these distances, you have to square them. Okay, so what did you say that number was here?
6750.
6750 equals 2x squared. Okay, so then you're going to divide both sides by 2.
3375.
What is it?
3375.
Okay, so 3375 equals x squared. And then
50.
basically you're just going to have to take the square root of that.
58.09.
How much?
58.09.
Okay. So be prepared for doing calculations like that because they'll expect you to be able to know how to do that. Okay, next question here. Now, basically that's what this one is down here for the next question. If a point source produces a rate of 50 MR at 1 foot, at what distance would you have to have it at to 2 MR per hour? Okay, so that's just the type of question that we just did. So you have 50 MR. So again, I1 D1 squared, I2 D2 squared. And again, this is probably the better way to remember the inverse square law. Okay, so we had 50 MR, 1 foot squared is equal to 2 MR x squared. Okay, so basically you have 50 equals 2x squared, divide both by half, you have 25 equals x squared, so therefore
Square root
5.
take the square root of both of those.
So 5.
Yes. So that's how they got 5. Now, again, the questions are probably simple enough where you can figure them out in your head. But they also make them complicated enough to where if you made a mistake, there would be an answer there for that mistake. So they really think this out when they put these questions in there. Okay. The next thing here, if the radiation intensity of a point source at 0.5 meter measures 36 MR per hour, at what distance will this intensity be halved? Okay, so again, same type of a situation. 36 MR times 0.5 squared. Now, equals 18, right?
36 divided by 2 is 18. That's half.
Well, we have, okay, 36 MR per hour at 0.5 squared is equal to 18, because we're having that, x squared. Okay, and I'm sure if you go through the calculations, you'll find that it's 0.7 meters. But like I said, get used to these, because you will definitely see something like this on your boards. They also like half value layers for some reason. On this thing over here, what they're trying to show you is, okay, you've got 500 MR or 500 MR per hour at 3 meters. What's the radiation at 1 meter? Okay, there's a couple ways to look at that. You know, just looking at that, you're cutting the distance by a factor of 3. If you square 3, it means that it's going to be 9 times more intense. I never like to take chances when I'm doing questions for my board exams. So even though it's obvious to me that it's going to be 9 times the radiation does, I still like to figure it out just to satisfy my, you know. When you have your adrenaline flowing and the pressure of timed test taking, you make mistakes. Okay? And what happens is a lot of times people will just look down there and they'll say, oh, you know, that's the correct answer. You know, make sure you look at all the answers. Make sure you completely read the question. Okay, and then it says if the distance between a radiation point source and the survey meter is doubled, the measured radiation exposure rate. Okay, if you double the distance, 2 squared is 4. Okay, so it'll be 1/4. So that's why they have it here reduced to 1/4 of the original exposure rate. What if I cut the distance in half?
Intensities.
Increases.
By what? By 4. Yeah, if I'm at 4 feet and I go to 2 feet, we cut the distance in half, so it's going to be 4 times higher. Okay? Now, good question here. All of the following statements about half value layer are true except it reduces the intensity to half the original value. Okay. 1/2 value layer of lead will absorb the same amount of radiation as 1/2 value layer of aluminum. That's true. Just the aluminum will be much thicker though, right? 1/2 value layer absorbs 50% of the photons emitted from the source. That's true. 1/2 value of lead is the same thickness as 1/2 value layer of aluminum. No.
That's false.
And here's the other thing. Okay, different energies of radiation have different half value layers. So obviously, the higher the energy of the radiation, the thicker the half value layer. In fact, in radiography, that's how we determine the quality of the radiation beam. We measure its half value layer, and then we have a chart that tells us what the energy of that X-ray is. Okay, that's a calibration thing that we do to make sure that the X-ray machine is putting out the proper X-ray energy for procedure. But the same thing is true with us. Okay, if you have seen the what's the difference between the tungsten thickness that we use for technetium versus the tungsten thickness we use for PET imaging?
Much thicker.
Thicker.
Yeah, usually it's about 7 millimeters for technetium, but it's about 14. It's about double for PET. Okay. Good question here. Now this is again what you're going to see. Fortunately for us, they don't expect us to know half value layers for certain energies of radiation. So they're going to give you questions something like this. Half value layer for lead is 0.3 centimeters. And that's true. That's about what it is. 3 centimeters of lead. What is the minimum thickness of lead that is required to reduce the exposure from 12 MR to 2 MR? Okay, there's a couple of ways you can figure it. The quickest way is to say, okay, 1/2 value layer will reduce that to 6. Another half value layer will reduce that to 3.
So that is 3 half hours.
Yeah, about 3, a little bit more than 2 half value layers to get it to that. So that's why, okay, so 3.3 centimeters is 1/2 value layer, this is 2 half value layers, this is 3 half value layers, so that would be the closest correct answer. And then this would be 4 half value layers. Okay, does that make sense? So sometimes they'll get it close. Okay. If you wanted to calculate exactly how much, how could I know exactly how much I would need to get this particular reading?
The beer lamp, yeah.
Exactly. Yeah, and in that particular example, if you know, I had a bad day, okay, we want to get 2 MR per hour. We started with 12 MR per hour, and then it's going to be E. Now, it says here half value layer. Okay, so what do I have to do? Okay, the half value layer is 0.3 millimeters. Okay, what would be the linear attenuation of that? Huh? Okay, do you guys remember a long time ago we had talked about, we had a thing called half-life?
Did you say where?
I want to know what the linear attenuation is. Just like, okay, over here I have a half-life of technetium is 6 hours. Okay, but I want to know what the decay constant is.
Oh, it's
0.1155. 693.
Yeah, so 0.693 divided by the physical half-life. And then to calculate linear attenuation, it's 0.693 divided by the half value layer.
But you just did that for tech and the questions for Island 31.
Well, I wanted to show you that, no, the thing here is, okay, we're looking at the similarity between a calculating the linear attenuation and the decay constant. Okay, they're both exactly the same. If we were talking about I-131, then I would have 8 days over here, and then I'd have 0.693 divided by 8 days.
So then the linear attenuation would be 2.3?
Let's see, it would be, yeah, 0.693 divided by 0.3. So it'd be 2 point something.
2.3?
Yeah. So if you wanted to calculate the actual thickness of material that would bring it down to that exact level, rather than just putting 3 half value layers there, then you would have 2 MR is equal to 12 MR, and then E to the minus 2 point, what did you say that was?
2.3.
2.3?
Mm-hmm.
2.3x. Okay, and then you would divide both sides by 2. So then that would give you, and then the next thing we would have to do is use the natural log. Yeah, you get the ln value of 1. So the ln of 1 is what? 0? Okay, so 0 is equal to 12.
No, 6. 0 is equal to 6, because 12 divided by 2.
Oh, yeah, right there.
Oh, that's right, yeah, 6. That's 0 though?
Yeah.
Log of 1 is 0? ln, the natural log of 1 is 0?
Yeah, the natural log of 1 is 0.
Mm.
Shouldn't the answer be 0 then? Anything divided by 1 multiplied by 0, 0?
Yeah, well, let's see here. Probably, yeah. Of course, it shouldn't though, because something isn't right here.
Other than 2.7, we take the
No, 2.31, that's right.
What is it?
2.31, you have 2.3, that's correct.
Now, what I'm worried about here is if you take the ln of 1, it
That's,
shouldn't be 0.
that's
It should be
0.
minus something.
I do
The ln of
1
1
and
is 0.
then we get ln 0.
Huh.
But maybe if we do 1 and take the e to the x.
Oh, and
Well,
switch
no, we wouldn't be
it.
using e to the x because we would be using the we need to make this base 2.718, and the only way you do that is multiplying it by ln. E to the x is where you take this, you take base 2.718, and you make it base 10. So, yeah, I don't know, I have to look at that one, it's kind of... Okay, then the next thing, okay, over here, so half value layer is 60 at 1.25 centimeters of lead. What percentage of photons would be absorbed if you have 2.5 centimeters of lead? Okay, well, let's see here. You have 50%, and then what's half of 50%? 25. So that's where the 75% comes in. Okay. If you wanted to diagram it, graphically, let's say you had 100 photons here, and you had 1.25 centimeters of lead, you'd have 50 here, right? And then another half value layer, 1.25. So you'd have 25 that actually get through, so 75% were absorbed. So that's why they got that number on that one there.
The problem before, we were supposed to divide by 12.
Instead of dividing by 2.
Wait a minute.
We
Reduce it from 12 MR to below 2 MR.
We divided, when we set up the Beer-Lambert formula, we divided by 2, but we were supposed to bring the 12 across to the other side and divide the 2 by the 12.
I don't think so.
It makes sense because we did that every time. We would always
Well,
get
okay,
one
because it
different.
says, okay, we have an exposure rate from the source that's 12 MR,
So that's I1.
and then we have E to the minus, we said point
But
2.3.
2.3. X. We wanted 2 MR over here. 12 into 2 divided by 12.
But then
You know what, you're right, we need to divide the 2 by 12. Shoot, I divided by 2, sorry about
Because
that.
if we did that every time, we would always get one on the
Yeah, I screwed up there, guys. We need to divide both sides by 12 to get that, so then now that'll work. Okay, so that's going to be roughly 0.125?
0.16.
Okay, so 0.16 is equal to,
And then we can actual log of that, right?
yeah, then hit the ln of 0.16. Okay, and once you hit the ln of that, then you can get rid of the e over here. Okay, so now basically all you have to do is take 1.83 and
You
divide
can
it
get
by...
rid of the negatives, right?
Yeah, you can get rid of the negatives too if you want.
So 1 divided by 2.3. So 0.77.
Yeah, so 0.77, and so rather than, if you wanted an exact number, that would be 0.77 instead of 0.9. But for our purposes, that was the closest one.
Isn't this when you told us probably a couple of months ago, that say if it cuts 12 and it goes to 1 3 centimeter, you would get 6, and then you go to another 3 centimeter, or 1 3 centimeter, you would get 3. You could choose to do that and see the longer way you just did.
Well, remember when you use the Lambert-Beer formula,
Takes into
It's gonna be-
consideration
Not quite
that's-
yeah, it's not quite right, it's not going to be exact. The Lambert-Beer formula takes into account, remember what we call side scattering and back scattering. So it's always going to be reading a little bit higher than what you would normally expect. Okay, are we having fun? Is this helpful?
Yeah.
Yay, isn't it better than taking a test?
Oh,
I think it's great stuff. Okay. Which of the following radiation monitoring devices is best suited for a patient who's received 150 millicuries of I-131? The portable ionization chamber, remember they call it a portable ionization chamber because it works in what region? The ionization or saturation region. Okay, normally you probably won't see QD pi on there. Okay, QD pi was a term that was their top secret code for ionization chambers during World War II when they were making the Manhattan Project. Okay, and also for the
Still a good name for the detector.
yeah. Okay, now here you go over here. 20 millicuries of technetium. Medurate urinates on the imaging table. Which of the devices would be the best for looking for residual radiation contamination? Okay, so remember that the Geiger-Müller is many, many times more sensitive than an ionization chamber. Sometimes I'll ask you a question of which of the following detectors has the avalanche effect. Okay. Remember that a Geiger counter, the electron that's knocked off by the radiation, it's amplified so much that it knocks off other electrons on its way to being detected, and then those knock off some, and so basically all of the gas on the inside of that detector discharges. That's why it's more sensitive.
What's that resolving time?
Yeah. And then there's the, remember the resolving time is normally how long? The resolving time is when the positively charged atom is going to the walls of the chamber to pick up another electron so it can detect another radiation event. Okay, so that time that it takes is your resolving time. During that time there's no detecting of radiation. Okay, who remembers how long it is? Miss
60
Cynthia?
seconds.
How much?
0.2.
You're close. No,
One.
about 100 to 400 microseconds. Okay, now the reason why that is important, okay, first of all from the standpoint of, overwhelming your detector, because if you guys walk into a high radiation area and you have a Geiger counter, chances are it will either detect nothing because the gas never has an opportunity to recharge. In other words, radiation is constantly ionizing the gas in the tube, so it never has a chance to fully recharge, or you're going to be getting about half of what is actually there. Because, in other words, it'll recharge to a certain point, and then as soon as the next radiation event hits, it goes back down. So you got to be very careful which device you use. Okay, but when the gas starts wearing out, the gas in those tubes gets broken down by the radiation. So one of the things that they measure when they send it out for calibration is what is the resolving time. So as I said, 100 to 400 microseconds is the normal time, but if that starts getting longer than that, then they'll probably have to replace that little gas cartridge.
So in a high radiation area, you'll be better off using the QD pi?
Yeah, remember that a detector that works in the ionization region only measures what we call primary ions. So any radiation or any ion pairs that are produced by the radiation event itself are what are detected. There is no amplification. Okay, there are two areas in our radiation detector.
Gas amplification.
Yeah, but they use gas amplification.
Which ones are those?
Well, definitely GM. Okay, GM uses that, but the proportional region. One of the things about the proportional region, we use it to differentiate what types of radiation are present. So remember we have, what's this first region?
Recombination.
A recombination, and we have a plateau. Okay, this is the ionization saturation. This is where most of our detectors work. Okay? And then we have this thing here. Now, this is the proportional region, and if I was looking at gamma rays, they would look like this. But if I had beta particles, they would look like this. If I had alpha particles, would look like this. Now, in some books, they identify this location where they all come together as another region, and they say this is the region of non-proportionality. I mean, I wouldn't worry about it because most books don't use that anymore. But then this next plateau is your GM region.